Absolutely gorgeous, my friends. Okay. So, here's, the quiz is done. You've all got 10s on it, yes? Yes. Now I want you to understand, oh, thank you for this. Thank you for labeling that too, Christina. I should have put that under there. These are the X bar values you're getting on the horizontal, and the frequencies on the vertical. Thank you, 100% correct. So, why did I have you put these on the board like this? What's the point of having these on the board like this?
So that we could see a representation of the different distributions.
Good! Excellent. These are not the distributions of the populations. I gave these things a clever name at the very bottom of the quiz. I underlined it bold because it's a term we use in 244 a lot. It's a term we don't use, we just learned it today, actually, right now. It's called the sampling distribution of the averages. So in other words, when you guys do an experiment and you calculate the average of whatever you've done, whether it's a probability, whether it's a weight, whether it's a temperature, whether it's a length, whatever, that center, that average sample that you just got, or that sample average you just got, falls into a distribution. And that's what you guys just did. You built a beautiful set of these distributions over the course of 50 or 75 trials. That's why I had your group together, because chances are your distribution of the individual group would look a little more varied than the distribution of the overall group here. Good. What's the first thing you notice about all of these graphs? Every one of them is way more bell-shaped-ish than the original distributions were. And remember, only one of the original distributions actually kind of looked bell-shaped. And it was your guys, it was the red one. The red one, which now, well, we'll come back to that, Christina. That's a very good point, because Christina's point is the red one doesn't look bell-shaped at all anymore. My contention is, it's because of the way I scaled the horizontal axis. I guarantee I could make it look bell-shaped if I broke the horizontal axis up into smaller pieces and give it more detail. I guarantee that's wickedly bell-shaped, but I wanted to keep the scale the same for all of it. Thank you for that. So, like for example, the orange one over there. Look at that perfect, beautiful orange bell curve over there. Remember what the orange one looked like originally? It was bimodal. Here. It was bimodal. Okay, so there's the blue one, there's the yellow one, there's the green one, there's the orange one, and there's the red one, which arguably already looked bell-shaped already. So, for the first thing I wanted you to all notice was that as soon as you ignore the population and go to your sample, and you have to ignore that population and go to your sample, of course, because that's what you get. You get your sample. You get your sample, and your sample is going to be bell-shaped. Crazy. Why? Why? Give me a reason as to why. For example, let's talk about orange for a second, just for a moment. The high value on orange, let's put orange back up for you guys. The high value on orange was 10. There was quite a bit at 9, right? Quite a bit, well, not so much at 8. And then there's a gap, and then there's quite a bit at 4. So there's a lot of 4s and a lot of 9s in the population, but 4 and 9 in the sample falls off. Why? Why does that happen? Why does that happen? And you got to remember, and this is why I'm so glad, Christina, you did this. This is the value of the sample average down here. Go ahead.
Because the clumping and whatever of being actually random is just more
It's definitely a clumping. Yes, it has to do with that. So that's good. I wasn't thinking about that. If you think about the individual 100 rolls that you guys did, and we actually had a sub-discussion about this with Patrick and Nick a few minutes ago. If you think about the 100 rolls that you guys did, chances are, on average, you saw every one of the 36 sums 3 times. On average, because that's about 108. 3 times 36 is about 108. So you would have seen all the rolls pop up. But the problem is, in order to see an average of, say, 9, right, you'd have to get either 4 9s, or 2 8s and 2 10s, or blah, 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 some combination that averages to 9. Well, the problem with that is, that's not that unlikely, but the problem is there's so many numbers down here that are messing that up. For example, 2 4s, or 2 2s to get a 4, or something along that, or the 1 and the 3. As soon as you roll a 1 in this guy right here, the chances of getting a 9 are essentially ruined. Essentially ruined. So the idea is the extremes that happen in the population are extremes. They're far away from average. In order to get them to have an average extreme or an extreme average, you have to get that extreme value 4 times. Well, that's the definition of an outlier. It shouldn't happen all that much, right? So the outlier shouldn't happen. Who's to think they're going to happen 4 times in a row? These guys asked a great question. In the red distribution, 9 is the most likely occurrence. But they never saw 4 9s in a row. And we had a little discussion about it. You guys did. You guys did, they didn't. But here's why. In order to get 4 9s in a row, 9 happens 9 times out of 36. That's 25% of the time. That's 1 in 4. In order to get 4 9s in a row, that's 1 in 4 to the 4th power. That's 1 in 256. So although a 9 is the most common roll, rolling it 4 times in a row is actually pretty uncommon. Does that make sense? That's what's kind of going on with these distributions. The things at the extremes, and when I'm talking about extremes, I mean far away from average. The things that are far away from average aren't happening on average. Therefore, having them replicate 4 times is even more unlikely than them even happening 1 time at the beginning. So when you look at, say, the yellow distribution, I'll pick on yellow now. Yellow has an 11 out here, yeah? Now where's yellow? Yellow's over here. Notice, nobody's even close to 11 in the yellow. Well, of course, in order to average 11, you have to roll 11 4 times. The chance of that happening is even worse than rolling 9 4 times. So you shouldn't see that. Nor should you see, although the 2 here is happening 4 in 36 times, which is 1/9. That's 11%. That's pretty good. But having it happen 4 times is pretty bad. That's a pretty bad probability. That's 1 to the, whatever 81 squared is. It's small. 1 over that is essentially not going to happen. Which is why you don't see many averages comparatively to the distribution. And also why that huge spike, boom, gets tempered down. Excellent. Now that's a bit of a hand-wavy explanation as to why the bell curves are there. The bell curve is there, yes. And as the number of trials goes off to infinity, the bell curve becomes perfect. We'll explore that on Wednesday. We're going to run out of time today. I don't want to rush to get it done. So that's 1. Okay, good, the bell curves. 2 other things I want you to notice. There's 2 other things I want you to notice about these curves. What else do you notice about them? Now that they're bell curves, Nick, go.
I was going to say they're skewed.
In what way?
Well, ours are skewed to the left, the red.
Which one's yours? Yours is red.
Yeah.
Let's come back to that, if you don't mind.
Okay.
If you don't mind, and I think any skew issue will be taken care of with a larger sample size. And I hate to do that. Give me 48 hours, right? I got to prove that to you. Yeah, I hate to do that, but give me 48. Nick mentioned skew. I think I can eradicate the skew worry with a larger sample size. Renee, go.
They all occur at different parts in x-axis?
Good. All the curves occur, the high points of the curves occur at different parts of the x-axis, yes? For example, the green one, the high point's somewhere in here. The yellow one, the high point's somewhere down here. Blue, somewhere in here. Red, somewhere over here. Orange, somewhere right here. Say it, Christina.
Oh, I was just saying like that one was actually between the 2. Like.
Oh, almost exactly, right? Exactly at 7. It should be. Now, exactly at 7. Take a look at the average in the population and how it relates to where the high point of the curve is. Coincidence? Hell no! That's exactly what it's supposed to do. So what that means is it's taken that goofy probability distribution in the population and giving you, what are you saying, Danny? What do you say? Every time. Every time. Which this means when we run a sample, on average, we are hitting the population average. Now, why is that good?
That improves the data.
Exactly. It means our data is actually accurately hitting what we're trying to look at. We want to know what mu is. Are we ever going to know it in reality? No, we're never going to know it in reality. We're going to know it experimentally on a sample. What this tells us is our samples on average hit the mu. I'm feeling pretty good about myself right now. You should be too. Because this means when we do a study, this is why, just FYI, this is why 244 exists. Because of this fact. Because of the fact that on average you're hitting mu with X bar. But Madeline's not convinced. She's like, okay, yes, on average you're hitting mu with X bar, but what if this was your sample right here? See, here's the problem. This represents at least 50 different samples, yes? At least 50 different samples. When you run a study, usually you get 1, maybe 2 if you're lucky enough to get enough funding to have a large enough study. So, yeah, it's most likely that you're going to land in here, because those are the highest bars. But how about these guys out here? Well, those are the guys that miss, yeah? Those are the guys that miss. This misses. That's the outlier in the sampling distribution. So, I would feel better if we had a curve more like the red one, yes? Where they were tighter in and there were actually, because remember, the red, you guys were 50 or 75 altogether? 75, and that's all I'm scaling, right? So that's 75, as is blue. But more of the data is closer to our average of 9.2 than is closer to the average of 8.2 over here. Renee, please.
Well, if the larger the sample size, the more meaning the outliers have.
Yes, let's go back to that. Because you guys have nailed 2 of the 3 things, and we'll get to the third one, then we'll call class for the day. We'll come back to it on Wednesday. First of all, the bell curve showed up. Hell yeah. Secondly, they're centered on the averages. Hell yeah, squared. Thirdly, what's happening to the standard deviation of this? What is, let's just, if you would, ballpark the standard deviation of this curve for me. Let's just do gorilla statistics. That's gorilla with a U, not an O. Like, not like, ooh, ooh. But like let's just, don't grab your TIs. Don't read them through 1-bar stats. Let's figure out what the standard deviation is on this curve. How could we do that? What do you think? And I haven't taught this to you yet, so if you're like, I don't know what the hell to do, that's okay. What do you remember about standard deviation on a bell curve? 95% of them are within 2 standard deviations. Can you approximate roughly where 95% of the data is on this curve? What if we just lop off the top and the bottom and call that 95% in the middle? That's probably pretty close to it, yes? This is why I made 4 pairs of dice. My goal was to get 100 rolls, but my classes are never big enough, which is probably a good thing, because you guys would get, it'd be like a big lecture hall in that case. So it looks like 95% of our data is between 5 and 10. So, right? So that would be the range of 2 standard deviations. Now that would be centered on 7.5, which is close to 7, but not perfect, but we're doing gorilla statistics here, yeah? So, if that is between 5 and 10, that means, what would 1 standard deviation be? What would 1 standard deviation be? Well, that distance is 5. Half of it would be 2.5, and then half of that would be 1.25, yes? Why am I doing half of a half? Remember, when Patrick said, thank you for that, by the way, when he said 2 standard deviations, that means you start in the middle and then go out 2 standard deviations to get to the endpoints. So technically speaking, that range of 5 is actually 4 little individual numerical standard deviations. So we're approximating that little s is just about 1.25. We'll come back to that. We'll come back to that, okay? We'll come back to that. Is it bigger or smaller than sigma?
Smaller.
It's smaller. Does this make us happy as researchers? Why not? I'm happy, actually. Tell me why you're not, though. Tell me why you're not.
I thought we were trying to get those to be fairly close to each other.
I want this, the average, to be close. Remember what standard deviation is a measure of? It's a measure of how far away. So if I can get them closer to average, I'll be happier. You see what I'm getting at? So, yes, I want this to be close to this, for sure. For sure. But I want this to shrink. I would love for that to be what, in fact? I'd love for it to be 0, because that means every single average would be on average. Perfect. Can't get that, unfortunately. So if I can shrink it, that's even better. Let's see if that holds across the board, yes? How about we just do this, just to make life easy?
Yeah.
It's gorilla statistics, yeah? So what's that? That's 3 up to 7, which is a difference of 4. So cut that in 4, that means our S is 1 in that case. Is it less than sigma?
Yeah.
Still pretty happy, still pretty happy. Okay, let's do it again. I'm gonna lop off, just lop off those, why not? 6 to 10 is 4 again, yes? So that's gonna be 1 again. Hot damn. Once again, it's less. Is it gonna continue? Let's see. Let's lop off that and that, okay? 8 to 10 is 2, divided by 4 is 0.5. Looking good, looking good. And now, and this goes back to that bell curve. If I gave this more detail, we get more of a bell curve. And then last but not least, orange, lop, 5 to 9. That's 1 again, yeah? So, 3 things that happened today that I'm pretty excited about. Number 1, Stacy noticed it right away. What was it?
Bell shape.
Bell shapes. Freaking awesome. Number 2, the bell shapes, Renee noticed it, that they're all centered on different parts of the axis. Where were they centered? Yes, the population average. Hell yeah. And number 3, and this is the tougher one to kind of talk about because
The standard deviation is smaller.
Yes, than the population standard deviation. This I'm calling this S. I'm going to put it in quotes, at least here so you can see it. It's statisticians actually call the standard deviation of a sampling distribution, something a little bit different. We'll come back to that on Wednesday. I want to do it right now. We don't have time. It's called the standard error. I want to explain why on Wednesday. But it changes as the sample size changes. And you just saw it. It got smaller. But what's cool is it gets smaller predictably. It's too hard to see with this because we were gorillaing it too much. So yeah, 1.25 is less than 2.92, 1 is less than 2, 1 is less than 2.65, but that was all approximations. I'll come back and I promise you, Nick, the skew will be taken care of too with an Excel sheet I've drawn up for you guys. We'll do it on Wednesday though. Okay, look? All right, we'll catch you then. Remember, you got one last quiz, stiff tier. And one last project, stiff tier. And that's it, thank you. Oh yes, and these quizzes, yes, take a little pile. I'll teach you guys some more tens, yes. Very important. Thank you, friends. Yes, if you don't mind re-racking the dice over here, that's perfect. Thank you, Skew. Take one more picture of that. Because it is just that good. You guys are artists. Those are freaking beautiful. I'm not gonna lie to you.